All right, hello. Today we are going to be showcasing this little mini microprocessor that we have built. All right, so I'll go ahead and identify some of the structures that we have here. Up here in the top left, we have our little control unit. All right, this is something that we will be controlling ourselves manually to step through this processor and to showcase what's happening step by step. But usually this would be its own separate unit in, say, a computer processor to do for us. And it will be constantly reading and writing on its own based on whatever instruction the computer is reading. So we will be controlling that ourselves. Here we have our device select, which we will just input an address to select between two different kinds of memory banks that we have here. We have a read-only memory. This is something that we will manually input values that we would want to send through our processor. And then we have our random access memory. The difference between the two is in the read-only memory, obviously we can only read data from here and send it through. In random access memory, we can read and write data. So this is where we will store results after we send our values through the arithmetic and logic unit. All right, and so this part up here is the processor. This is where our values that we have and send through practically gets processed and solved for. So that's all thanks to this arithmetic logic unit. We can perform subtraction, addition, multiplication, and I'll explain what this least significant for and most significant for means in a bit, and as well as some logic functions over here as well. All right, here we go. I'm going to show how this works. I'm going to multiply two decimal values, 10 and 6 together to get an answer of 60. Okay, so first thing is first we're going to want to load our values into the read-only memory bank that we have here. I'm going to go ahead and load 10 into ROM 0, and I'm going to go ahead and load 6 into ROM 1. Okay, and what we're going to want to do is load these values into the processor. So what we're going to do is select read because we're going to read into this. And as you can already tell, we have our ROM 0 here selected and getting a high value into this buffer. That's allowing only the value in ROM 0 to go through the data bus and into the processor. As you can see here, we have a value of 10. And what we're going to want to do is, because we're loading two values and we don't want to overwrite anything, we're going to load this into the register here. So I'm going to go ahead and enable B register and cycle the clock once. Therefore, we have our value of 10 there. And now we can't easily overwrite this value. So I'm going to go ahead and turn that enable B off, and leaving read on, I'm going to select ROM 1 by inserting address 1. And as you can see, this buffer is getting a high value, and we're only sending this value of 6 through. And as you can see, it is right here before the register, but it's not being loaded into the register. So we're going to bypass this by selecting B here. And as you can see, we are getting our value of 6 loaded into this A part here, into this arithmetic and logic unit. So now to perform the multiplication process, we're going to select both these modes here, 2 and 3. Because we are multiplying two 4-bit values here, we're going to 10 times 6 gives us 60. That's going to be more than 4 bits. So we're going to take the least significant 4 bits and we're going to write that into one register. And then we're also going to take the most significant 4 bits and write that into another register. And that's how we're going to get our value. So next, select the least significant 4 bits here. Okay. And as you can see, the multiplication has already taken place, or at least of the least significant 4 bits. And we're going to enable this accumulator here and cycle the clock once. Therefore, we won't ever accidentally overwrite our value. I'm going to go ahead and turn this accumulator out so that we send it through this data bus here. And we're getting a red value here because we should be on write mode. Okay. And now we want to select the correct random access memory to store our least significant 4 bits. So I'm going to select RAM 5 here. So I'm going to hit address 5. And as you can see, we have selected this register here. And I'm going to go ahead and cycle the clock once. And as you can see, we have our least significant 4 bits here as a value of C, or 12, which is correct. So I'm going to go ahead, turn this accumulator out off, and I'm going to turn right off as well for now. And we're going to do the multiplication of the most significant 4 bits here. So I'm going to select a value of 3. Okay. And I lost my value of 6. So I'm going to hit register 1 for that. Hit read, load that in there. There we go. And now we get our most significant 4 bits here. So I'm going to go ahead and overwrite this by enabling this and cycling the clock once. And then I'm going to send this out. Again, select write, and we're going to store this into RAM 6. So I'll select 6, leave that on, and then I'm going to cycle the clock one more time. And then perfect. We get our value of 3 stored into RAM 6. Okay, so this should equal 60, but it's in hex right now. So we have a value of hex 3C, I believe, which should equal in binary as 0011 and 1100. So therefore we have a value 1, 2 in the 4th, in the 8th, in the 16th, and the 32nd. So this 32 plus 16 is 48, plus 8 is 56, plus 4 is 60. So the math has added up. So that is how this little microprocessor works. As you can see, it is a little annoying to work with this control unit a bit because usually that's something that the computer does on its own very quickly. But when you have to be in control of it of yourself, you could see how difficult it can be to go from reading and writing. So as you can see, these little thick lines, these are our data buses. A data bus is simply just transferring a multitude of data bits through the processor and storing them and helping with the whole entire read-write process. Buffers are very important in this whole entire build. We always have to make sure that we are step-by-step not overwriting our registers or misplacing values, taking them and sending them where they're not supposed to be. Here, we use the buffers to make sure that we are selecting the right value at once and not accidentally sending 2 address values at once. So, and then like these buffers here, this is an example of making sure that something is not being written over. So that's the importance of buffers. All right, so this is an interesting question. Explain why it is useful in a microprocessor to only allow register changes to occur at narrow, regular intervals. So that's very important because computers are working on a very, very, very fast clock cycle. In modern computers, up to like 1 gigahertz frequency. There's 1 billion cycles per second. So it is very important that the clock reads at very, very fast positive clock pulses because everything was being read at the positive portion of the clock. So it has to be really, really fast so that the computer or the calculator can perform the math in a timely manner. So taking a look into this ALU a little bit more, we can see this is what the ALU consists of, and it even consists of a smaller unit here, this LB Mini, which stands for the logic block unit. So I'll go ahead and open that up too and show that. You can see there is a lot of gates that we are using in just this ALU component alone. These muxes, I believe, have 16 gates in themselves. This is 4-bit 2-to-1 multiplexers, so they have 16 gates in each and every one of them. As you can see, there's already 48 here, 49, 50, 51, 52, and that's just 52 gates there. And then we have another 16, 32, 48, 56. We already have so many more gates here, and then plus, 10, 20, 30 here. So overall in this whole unit, just this ALU arithmetic logic unit, we have nearly 100 gates being used. So using this hierarchical design, we can just really simplify things and make it look so much more neater and beautiful. So there's a lot more complications going on just in this arithmetic logic unit, and to have it stored in such a nice, neat, confined space makes everything so much more easier to work with and to read and to see. So anyways, that is everything for me. Thank you for watching.